Okay. Let's get started today. I'm going to remind you.
Monday is the big word test.
Yeah, vocab quiz on Monday. But remember, on Tuesday you will have a work day for your animal project. So hopefully everybody remembers what animal they have. If you forget, though, I do have the list, the master list up there. And before Tuesday, I will try to have some extra sheets in case you lost yours. I'm sure many people did. You didn't remember that? You have a lot of things where you have to come up with animals that you're going to do reports on? Huh. Fastest animal in the world. Let's talk about reptiles and amphibians, because our question of the day yesterday asked, what's the difference between reptiles and amphibians? Well, I actually didn't end up having time to look over these because my daughter was sick and I had to take the afternoon off yesterday. So I didn't see what you put yet, but we're going to talk about it. So there's actually not that many species of amphibians. I mean, this doesn't show all the species, but there's basically 4 broad categories of amphibians. There's frogs, toads, salamanders, and newts. And salamanders and newts look very similar to each other. Big Newton. Turtles are not amphibians. Turtles are reptiles. Okay, the major thing that is going to separate reptiles and amphibians is that amphibians have gills when they are young that turn into lungs. Okay, reptiles also have scales, and so if you put scales down, you're not wrong. Amphibians don't have scales. But the major defining factor, the major difference between amphibians and reptiles is that you can drown a baby reptile. As horrible as that sounds, we should say, I guess, that a baby reptile can drown, whereas a baby amphibian can't because they're going to have gills as they start out. So if you think about like a tadpole, right, swimming around, that thing has gills that's able to extract oxygen from the water, but then as it grows into adulthood, it grows lungs. And so that's the whole amphibian means part land, part water, and that's the whole thing. They start out in the water, but kind of like fish almost, but then they develop into land-dwelling creatures.
Reptiles are longer on average. That's what I thought.
That may be true, but that's not the defining feature. A crab is a crustacean. It's an arthropod. It's not even a vertebrate. They're much different.
Tortoises can't live in water, right?
Right.
Like the people that think they're saving turtles and they drop them in the water.
I think tortoises can swim for the most part, but they're not. I mean, yeah, tortoises tend to be more land-dwelling. They don't need to be around water. There's aquatic turtles too. But all of those, they have to breathe air. So just like whales are not fish, they have to breathe air. They can just hold their breath for a long time. Same thing with turtles and things like that. Now, turtles are interesting because in the wintertime, they can actually go down underneath the water and bury themselves and live for months there on the little bit of air that they have in their lungs. So they shut down all their metabolism. Most frogs and toads, I think actually all frogs and toads, they grow up, they all have lungs. But some species of salamanders actually retain their gills even though they develop lungs, so they're actually able to breathe, both through their lungs or through their gills, depending on where they are.
Could you make a human with gills? Like get the Sam's point?
Well, we all start out with gills. When you are an embryo, you actually have gill slits, and that kind of shows our And that's something we'll talk about down the way. That kind of shows our evolutionary history with some of the related organisms. But those go away over time. So could you somehow change our development in which we keep our gill slits and develop gills? I'm going to say possibly. I just don't know straight off the bat. Yeah, I don't know about that. Like a scuba tank? Yeah, I know what you're saying. An artificial gill would be pretty cool because it would extract oxygen from the water, and so unlike a scuba gear, yeah, you never run out. You wouldn't run out of air. You wouldn't have to come back to the surface. You just use it the whole time. So that would be a pretty cool invention if you want to get started on that, Sam. Artificial gills. All right, let's get started with what we're going to talk about today. Oh, that's right. I got into the, yeah. Once we get through this stuff, we'll check the homework and go over that. Kind of skating on thin ice there, Tate. So, for the longest time, people believed in something called spontaneous generation, the idea that living organisms can actually come from non-living things. And their evidence from this was just from daily life. If you leave a pork chop sitting out on the deck in the summertime, eventually you're going to see maggots crawling around on there. Right. So for a long time, people just thought, hey, when meat spoils, these maggots just appear. And so we call that spontaneous generation. But it has been since pretty much disproved. And Matt brings up one example from a guy named Reedy. I'm having a heck of a time today. So Reedy did an experiment where he took a piece of meat and covered it with kind of like a cheesecloth so that flies couldn't get to it. And showed that maggots would not develop on the piece of meat where the flies couldn't actually land on it, showing that maggots actually come from flies landing and laying eggs. And that wasn't actually obvious to people before that experiment because a lot of times you don't notice the flies or it doesn't look like they're doing much when they land, but it turns out that flies lay eggs all over the place, anywhere they can, hoping that some of those will develop into maggots, which then, of course, will develop into adult flies. Pet maggots. Okay? Well, maggots have to have something to eat, so meat or really any organic source, dead plant matter, feces. You go to a hog barn or something that hasn't been cleaned out for a while, there's going to be maggots all over the place, at least in the summertime. So, anywhere that those maggots can find something to eat and grow on, they're gonna thrive. But Reedy showed that they have to come from something. They have to come from the original flies to begin with. There's another experiment done by a guy named Pasteur. And you may recognize that name because he came up with the process of pasteurization that we use in getting bacteria out of a lot of different products, especially things like milk, where we want to make sure that they don't go bad, within a couple days. It's a couple days, a little bit of exaggeration, but so they have a little bit longer shelf life. And he did an experiment where he took a special kind of flask with a special shape. Okay, and people at the time thought that things spoiled just because the air, right? The air getting to them would just, make things grow in them and make them spoil. So he took a special kind of flask like this, and he put chicken broth in here, basically. Yes, this is a tube. And he had this special neck, and I don't know, I kind of horsed up on the drawing of it. Let me try a little bit better here. But it has a special neck that kind of comes down and then up again. That's slightly better. Anyway, the point is that the tube is completely open to the air, so air can get in there no problem. However, if there was any little organisms like bacteria that can't crawl their way up the tube, they wouldn't be able to get in the chicken broth. And so he took some of the flasks and he just left them, and he showed that they would grow stuff in them, right? They would grow bacteria and they would spoil. He took some of the flasks and he boiled them. And so by boiling them, he killed off any of the microorganisms that were in there, and then he let them sit. And those that were boiled never actually spoiled, never grew any microorganisms, showing that these things didn't just pop into existence out of the air. Because they couldn't get up the neck of the tube, they were never able to get into the broth and start growing there. And then there were some other ones where after he boiled and let them sit for a while, he took the flask and kind of inverted it a little bit, so a little bit of stuff ran up into the neck, into this part right here, right? And then he put it back, and then those would spoil. So he kind of showed that the microorganisms that were getting into stuff and growing all got trapped right here because, of course, they aren't able to crawl around. So he kind of showed that bacteria wouldn't get into things if they didn't have a way in, and they wouldn't spoil stuff. And there's actually, so this experiment was done in the 1700s, I believe, in France. There's actually some of Pasteur's flasks that have never spoiled. They're still sitting there with that original chicken broth type stuff in it. Yes. And to show that if bacteria can't get to it, it's not going to get that stuff growing in it. Okay, so these type of experiments paved the way and kind of pointed towards the idea of biogenesis. Okay, and biogenesis wasn't exactly a completely new concept. I mean, people knew up to then. You don't get another person unless two people have a baby. You don't have an elephant that just pops into existence. It has to come from mommy and daddy elephant. But there were a lot of questions with things like bacteria, single-celled organisms, and insects and that kind of stuff. So some of these experiments showed that even for bacteria and insects, life has to come from other life, pre-existing life. Okay, so remember when we talked about our certain circumstances for life, one of the things we said is life has to things to be alive have to be able to reproduce. Yeah, I think your seat's actually supposed to be up here. culty this morning. So, of course, this prompts the question, where did the first life come from? How did life, I mean, if life only comes from life, how did those first organisms show up? Okay, now in the fossil record, things point to life starting out about 3 billion years ago. So we have fossils dating back, and when we looked at those little mounds of bacteria and stuff like that, all our indications show that about 3 billion years ago we see the first signs of life on the planet. Now that doesn't mean that that's when it absolutely started. It just means that's the earliest that we have record of something that would be called life here on Earth. At that time, the Earth was a very different place. By analyzing gases trapped in rocks that were formed at that time from volcanoes, we actually see that the atmosphere was quite a bit different. There was almost no oxygen in the atmosphere, very little. Now, oxygen obviously is an important compound. In fact, it's an important compound to most all life. There are some bacteria that don't need it. But oxygen is an important compound because it's very good at causing chemical reactions. And that's why we need it inside us, is because all the chemical reactions that have to do with breaking down food require oxygen. But oxygen is actually kind of a hindrance for molecules forming because it reacts so easily with them. And so at this time where there was almost no oxygen, it was very different from now, and there was some, that gave an environment where chemical reactions could happen in a slightly different way. Okay, what scientists have been able to show in a lab is certain chemicals in a no oxygen environment, or at least a low oxygen environment, can self-replicate. And they do so by creating templates. So when you have chemicals floating around, as they would have been in the early seas, and those chemicals, and we're just talking about simple things, right? Off the periodic table. When the chemical reactions happen between those things, over time there are certain chemicals that can actually form up into chains and create templates that other chemicals will then come together in the same shape. And so that's an early form, or a very simple form of a type of reproduction, where you have one type of chemical. Now, I mean, these things would not be anything that we would consider life at that point. What's that? Yes. Okay, but it does show that amino acids, which of course are an important part of living organisms, those types of chemicals can actually form on their own, and then they can have other amino acids that form off of that template, and we get kind of this self-replicating system in the chemical reactions. Does that mean this is how life has started? No. We don't know for sure. We may never know for sure. But it gives us an indication that those sort of things could have been the start, the seed of very simple organisms, where then you had some sort of a cellular membrane that is created around those chemicals, and those would last longer and be able to reproduce more often. And that could give the rise to the first types of things that we might start to call life. Okay, but like I said, 3 billion years ago, it's really hard to know exactly what happened back then. All we really have is some ideas on how those things could have been started. There's another idea with the fun name of panspermia. Okay, sometimes when big asteroids will hit a planet, it'll actually fling rocks off of that planet. And there are certain organisms, certain types of bacteria that we've shown that can actually survive in space kind of indefinitely, and then if they get to a habitable environment, restart their lives. And so it's theoretically possible that you could have had some rock that slammed into another planet, like Mars or some planet in another solar system, and then rocks that got flung off of that had simple-celled organisms, and those rocks eventually fell to Earth and started growing here. Now, of course, that doesn't actually answer the question, how did life start? Only just maybe how life got its start here on Earth. This is another thing we probably will never know for sure, but it is an idea, and it is definitely possible. It is physically possible from all the things that we know with the life that is here on Earth, simple-celled organisms, and how physics works when a big asteroid hits a planet. Okay, so these are just some ideas about how things may have started to create the first things that we might call life. Then there's one more theory that I think it's worthwhile talking about because you hear about it sometimes, and that's called endosymbiosis. Now, endosymbiosis doesn't have anything to do with how life would have first started, but endosymbiosis is a theory of a hypothesis of how maybe eukaryotes got their start. Now, what type of organisms are prokaryotes? Yeah, bacteria, single-celled, very simple. Eukaryotes, of course, are much more complex. You guys all did your cell models for eukaryotes. Eukaryotes have all sorts of membrane-bound organelles, like mitochondria, like Golgi apparatus, like endoplasmic reticulum, a nucleus. All of those things are things that exist in eukaryotes that do not exist in prokaryotes. So endosymbiosis is the idea that eukaryotes may have got their start, or the first simple eukaryotes may have come about by prokaryotes that engulfed another prokaryote. So one type of bacteria engulfs another type of bacteria, but for whatever reason it doesn't actually break that bacteria down as it probably would be trying to. But that other bacteria that it engulfed is still kind of living its life inside the other bacteria. So think about something like a chloroplast, right? The whole point of a chloroplast, or what it does for a cell, for a plant cell, is it is able to absorb sunlight and create food from that. So if you have one type of bacteria that is able to do that on its own, to absorb sunlight and kind of use that as its fuel, and you have another type of bacteria that goes around eating other things for its fuel, and it absorbs that first type of bacteria, but it doesn't actually kill it and eat it, then this food that's produced by that one bacteria could be shared inside the bacteria that engulfed it. And so that gives an idea of how maybe those first types of organelles turned out, by being absorbed by other types of bacteria, other types of prokaryotes, and then using them instead of destroying them and eating them. So perhaps the first organelles were formed from prokaryotes that were eaten but not digested by other prokaryotes that lived at the time. Okay, I think that's all we need to cover here today.